Hello everyone, welcome back. Let's try this again. I'm having some trouble saving my videos, so I'm going to keep this one kind of short. They're going to be in 3 segments. So let's come back to our section on the moles of, why do we give a crap? All right, our moles section, it's really important because we've got some major ideas here. Starting in 1959, this idea of the mole was agreed upon. Okay, and then in 1980, the actual definition was agreed upon. And that's the definition I'm going to start with. And that's the definition that you've probably heard from high school chem or intro chem or even just last year's gen chem. Now, this was updated in 2019, just literally last November. So we'll kind of hit both of these and discuss both of them. None of it changes your calculations. It's just a different vocab. All right, so why do we give a crap? Well, let's put some perspective on it. Let's go down to a question I asked you guys right before spring break started. And let's look at, what if your final was to actually make sodium chloride in the lab and then eat it? Make it and take it, okay? So if that was your final, that would either be a really good thing or a really bad thing. So let's go back to our unit 2, the unit that we just did, and let's talk about how sodium and chlorine even come together. So we know from unit 2, what kind of bond was that? That's an ionic bond. So sodium, if it gets close to sodium, or chlorine, what does it do? Boy, it just gives away an electron for free, just gives that away. And then chlorine is right there and takes it. It literally takes that electron. We saw that even in a video right before spring break. So this is awesome. This is completely up to Mother Nature. This is your fixed ratio. Oh, pen mishap there. This is our fixed ratio. Okay, there's nothing you can do to monkey with that. That is up to Mother Nature. So then if this is your final, well, this is easy. Just count 1 sodium for every 1 chlorine and you're in business. That would be the best final ever. You just come in, grab a box of sodium, count out 1 chlorine, done. Except this is the huge dilemma that has plagued chemistry for hundreds of years, and that is that can you actually see an atom of sodium? Can you actually see it? Ooh, creepy eyeball. No. What about an atom of chlorine? Can you see it? Heck no. So, since we can't actually see either one of those things, how in the world are you going to count them? Okay, well, wait, Dr. A, what's up? Why don't I just weigh out 1 gram of each of them? That would be awesome, right? Weighing is super easy in the lab. You can take a couple minutes, just go right in the lab, use that balance, done. 1 gram, 1 gram. Okay, that would totally work if they were the same thing, but they're not. Sodium is completely different than chlorine. Our sodium atoms weigh different. In fact, they weigh less than our chlorine atoms. They weigh different. So now, if that was your final, sweet Jesus, what's going to happen? Well, you're either going to have Mother Nature is going to govern this one. So you're either going to have leftover sodium or leftover chlorine. Well, what's going to happen if you have leftover sodium? Well, okay, that's supposed to be a flame. We know sodium, when it hits water, lights on fire. What happens if you have leftover chlorine? It's a fatal gas. So you're sort of screwed on either end. You really kind of got to get that count right. And you're probably thinking, this is just an archaic way of looking at things. But so many of us end up in science or healthcare or all kinds of places where this is essential. You are going to be making stuff, mixing stuff, making a solution, injecting it into somebody, feeding it to them. At some point, this is going to touch your life somewhere. It's actually a pretty big idea. So how in the world do you tackle it? Well, let's go back up here and let's look at our definition for our mole. Okay, I'm just going to erase this part. Now let's give our official definition. Starting in the 80s, let's define a mole. So a mole has had many definitions, but this one and this idea really stuck. Okay, this idea is that 1 mole of any substance, it has to be related to any substance, but the 1980s definition picked carbon in order to define the mole. Okay, now our mole we're going to apply to any substance. But let's define it first for carbon. Okay, so what is the point? Well, the point is somehow to be able to actually go into the lab and have something that is easy to weigh, and then know from that weight what the count is on how many atoms you have. That is the point of a mole. Man, that's so flippin' important. I need to say that again. Okay, what is the point of a mole? We need something that we can see and that we can measure. And that is easy to weigh something. It's one of the easiest lab techniques we have. But we know from our bonding and how chemistry works, man, we have to know how many atoms. Otherwise, we have no idea what's left over and what harm can happen or not harm. We have to know how many atoms are actually there, but of course, we can't see it. Otherwise, this whole thing would be so easy, right? So, how do we make that happen? Our 1980s definition was to take carbon 12 and to set that equal to 12 grams. So 1 mole of carbon 12 is equal to the weight of 12 grams. Okay? And then how many particles are in there? So that's the 1980s definition, was to call this a particle. 6.02 times 10 to the 23rd particles in that carbon sample. So we know that that particle is an atom, but the mole can be any particle. Okay, so let's make a connection here. This is awesome. Let's make the connection that that 12 grams is, this is a sparkle pen moment, is the atomic weight of carbon. And then let's make the connection here that our count piece is Avogadro's number. Okay, so this is awesome. This is a way to now connect all of our elements, right? Everything is listed on the periodic table. And are they all the same? No. And how are they different? Their weight is different. So all of our elements on the periodic table, their atomic weight is equal to 1 mole. And that 1 mole has Avogadro's number of particles in it. Okay, that is super deep, and I need to say that again. Let's write that down. Okay, let me erase and give myself a little bit of space. Grab your periodic table and your calculator because we're about to put this to use. All right, so let's say that again. This is super important. Any element, 1 mole is equal to its atomic weight and is equal to Avogadro's number. Okay, I better capitalize that. That is a name. Okay, so that means your periodic table, this is so exciting, your periodic table just turned into one huge unit conversion table. So in fact, grab your periodic table and let's add a unit to it. Your atomic weight, the unit, is grams per mole. That's a sparkle pen. Ooh, let's go a little bit that one. All right, grams per mole is the unit on your periodic table for all atomic weights. So your mole needs to be in the middle of all of your calculations. You're going to go from atomic weight, something that you can see and measure, to a mole, to a count. This is how you can go weigh a substance and know how many atoms are in it. It's actually pretty genius. It's pretty cool. And even though it seems sassy and the theory's kind of deep, at the end of the day, we've done this already. This is a unit conversion. In fact, the first half of this unit, all we're doing are unit conversions. We're just going to calculate unit conversions. So let's list out under here real quick. So let's just take sodium. Okay, let's take sodium. Atomic weight, 29. Look at your periodic table, find your atomic weight for sodium. That atomic weight is 29. So what is the unit on that? What that means is that 29.9989 grams, you go to the lab, you weigh out that much, and now you know exactly how much is in it. So 1 mole of sodium, you know you've got Avogadro's number. Okay, which particles is the 1980s definition. The 2019 definition is called elementary entities. I'm going to go out on a limb here and abbreviate that EE, even though EE tends to stand for something else. I'm going to wing it. Okay, so then that 1 mole, you go to the lab and you measure this many grams, and you know exactly how many is in it. Easy to weigh, count of particles. Okay, this you can weigh, and this is your count. Genius. All right, let's stop here and then let's do some